Okay, welcome to this video on carboxylic acids and derivatives. And there's the syllabus that we're following. Let's do the first bit, recall the reactions by which carboxylic acids can be produced. First one is oxidation of primary alcohols and aldehydes with acidified potassium dichromate or acidified potassium manganate. So what we have here is, let's start off with a nice easy alcohol. This is ethanol. Okay, and it can be converted into ethanoic acids. All right, this is an oxidation because it's gained oxygen. And how do we do it? We do it with, let me try and get the colors right. This guy, K2Cr2O7, and it's acidified and heats. Okay, I'll talk about that in a minute. Or we could also use the purple stuff, which is potassium manganate, acidified and heat. Okay, and both of these are oxidations of the primary alcohol. Now it must be a primary alcohol because a secondary alcohol won't oxidize to the carboxylic acid. So we don't want to stop midway through at the aldehyde, so we use reflux for this. Okay, so let me get my reflux apparatus. There it is. Okay, let's get rid of that for a minute. Okay, so we're going to reflux this. Now, the reason we reflux this is because we want to go all the way from the primary alcohol all the way past the aldehyde stage, and then from the aldehyde to the carboxylic acid stage. Okay, so if I wanted to stop at the aldehyde stage, I just use distillation. Okay, but if I want to go all the way to the carboxylic acid stage, I would use reflux. And here it is on the right. Okay, let me try and change colors here. Nice blue color. Obviously, what will happen is the aldehyde will form. It will rise up here, but it will condense in the condenser, and it will fall back for further reaction with my oxidizing agent to form the carboxylic acid. Okay. Obviously, we can also, if we're given an aldehyde, we can oxidize the aldehyde to the carboxylic acid as well. And we would use reflux again. Why would we use reflux? Because if you don't use reflux, the aldehyde will evaporate off, okay? And we don't want that. So, as the syllabus says at the top here, oxidation of primary alcohols or oxidation of aldehydes would acidify potassium dichromate or acidified potassium manganate and reflux. All right. Now, we all know the color changes, or we should know the color changes. If we use this, this potassium dichromate, starts off as this orangey color and it ends up as a nice green color. Oh, yeah, it does. And it goes to the chromium 3 plus. So the color changes here are obviously orange to green when it's done its job. All right, and we oxidize the primary alcohol. For manganate, it starts off as purple, potassium, acidified potassium manganate, and it ends up as colorless. I'm going to show colorless of that color as the Mn2 plus ion, and this is purple, and this goes to colorless. Oh, didn't change, but never mind. Okay, so that's the first bit done. Okay, that's one way we make a carboxylic acid. We oxidize a primary alcohol, or we oxidize an aldehyde. Number two, hydrolysis of nitriles with dilute acid, or alkali followed by acidification. Okay, so the second way, that's the first way we make a carboxylic acid. The second way, let me hide that guy for you for a second. The second way is we hydrolyze. We use hydrolysis on nitriles. Now, we did a tiny bit of this in class. Okay, so first of all, what is a nitrile? It contains this functional group. This is the nitrile functional group. Okay, and let's have a nice nitrile. Let's use 3 carbon atoms. So there's 1, there's 2, and there's 3. Okay, so this one is going to be called propane nitrile. Okay, and it's a member of the nitrile family. Right, now if we heat this up with a mineral acid, sulfuric acid, for example, and heat. Okay, by the way, let me go over here. What are the mineral acids? Mineral acids are the ones we use in the lab: sulfuric, hydrochloric, and nitric. Okay, these are known as the mineral acids. If you like, they're the inorganic acids that we use. Okay, and it's to differentiate them from carboxylic acids. We call them the mineral acids. All right, so these ones are used, and as you all know, they're all strong. Okay, and that means they dissociate fully. So if we heat a nitrile up with a strong or a mineral acid, okay, the nitrile will undergo a process called hydrolysis. Okay, let me write that down. This is known as a hydrolysis, and you will get the corresponding carboxylic acid. Okay, so if I started off with propanoic acid, I'll end up with, if I ended up with propane nitrile, I'd end up with propanoic acid, and there you go. So propanoic acid. Now, interestingly, what does the syllabus say? This is called an acid hydrolysis. Okay, why is it called acid? Because we used an acid to do it. Okay, interestingly, we can do exactly the same reaction. Okay, but we can use base hydrolysis. So let me do exactly the same thing. All right, here we go. Now I'm going to use base hydrolysis. And I'm going to start off with my propane nitrile again. And this time, let me get rid of that one. Changing colors is not as good as it used to be on this. And I'm going to use sodium hydroxide now. Aqueous and heats. Okay, and this one we call base hydrolysis. Okay, you get exactly the same thing, but there's a problem, as you can see. So we get the propanoic acid, but then, as you know, the propanoic acid will then react with my base here. So in fact, I won't get propanoic acid, I'll get the salt. Okay, so this is sodium propanoate. Okay, which is the salt, isn't it? Now, I don't want the salt, I want the carboxylic acid. So if you do this one, acid hydrolysis, you get the propanoic acid. But if you do base hydrolysis, number 2, you get the salt, and we don't want the salt. We want the acid. So then the salt must itself be treated with another mineral acid. So you're going to treat this with HCl or any acid, any strong acid really. And what happens here, let me get rid of that, I don't know why I put that there, but let me get rid of it for now. What happens now is because propanoic acid is a weak acid, it will reprotonate. Okay, and protonate is to gain the proton because it's weak. Okay, so the proton pops on here and we get the acid back, and so we get my propanoic acid. If you ever have the salt of a weak acid, okay, to convert the salt of a weak acid back to the acid, okay, all we have to do is we have to add a strong acid. Okay, and what happens is, let's have a look. Let's see if I can do it in a different way. It's nice pink. That gets reprotonated. In other words, a proton jumps on it from the strong acid, and you regenerate your carboxylic acid. Okay, so which way is better? Hydrolysis using an acid or hydrolysis using a base? Well, they're both equally as good as each other. But the thing is, if you use hydrolysis of a base, you have to remember to add acid afterwards to regenerate the proton, regenerate the carboxylic acid. If you just go straight for acid hydrolysis, you get the acid straight away. Okay, and that's often easier, kind of thing. But you have to know both, obviously. All right, let's go back up here. What's next on the syllabus? So we've done A. Let's tick these off, shall we, as we go along. Let's use a nice black pen. We've done A and we've done B. Hydrolysis of esters with dilute acid or dilute alkali, followed by acidification. All right, it's the same idea. Now we did this in class, okay? And now I said I'd do this for completeness. Let me get rid of my sneaky white solid here. So another way we can generate a carboxylic acid is by the hydrolysis. We do it by the hydrolysis of an ester. Okay, so let me draw my ester. 1, 2, 3, 4, 5. I'm going to have a 5-membered ester. Okay. Now, as I mentioned to the upper 6, I don't mention it to you, some of these videos you can actually put on double time because it takes a while for me to draw things. Okay. So if you put it on ×2 when you're on YouTube, you can get through the video in half the time. This particular ester, well, the alcohol here is ethanol, so this is ethyl, and the acid is propanoic acid, so this is propanoate, isn't it? Ethyl propanoate. This is my ester, and it's going to snap here, okay? And it's going to snap right in the middle, and over here we're going to do one thing. Over here we're going to do another thing. On the left, I'm going to hydrolyze it with an acid. It must be aqueous and heat, and on the right, I'm going to hydrolyze it with an alkali and heat. Whatever I do, okay, they're both hydrolysis. Now it snaps there, so let me go regenerate my color. So on the left, I'm going to get this. Okay, CO, and now I'm going to leave that blank for a mysterious reason. Okay, and now I'm going to do the other part, the alkali bit. Sorry, not the alkali, the alcohol bit. Okay, so the acid gets what back? It gets an OH, and the alcohol gets an H back. And as you can see, that adds up to H2O. That's why it's known as a hydrolysis. All right, so if we do, on the left, if we hydrolyze with an acid, we get the carboxylic acid back and the alkali. And on the left, this is known as acid hydrolysis. All right, now on the right, we call this base hydrolysis. Okay, right, 1 second. Let me pause the video for 1 second because I've got to go and get something. 1 second. Okay, so we're looking at base hydrolysis now. So you get exactly the same thing. You get the carboxylic acid. Okay, let me draw my alcohol first. You get the alcohol. Okay, and you get the carboxylic acid. But if you were concentrating above, you won't get the carboxylic acid, will you? Because the carboxylic acid will then react with the sodium hydroxide. So you will get, in fact, the salt of the carboxylic acid. I don't want the salt of the carboxylic acid. I want the carboxylic acid itself. So what do? I add a mineral acid to this. Okay, and it converts it to not the salt, the propanoic acid. Okay, so you have to remember, if you use base hydrolysis, you'll end up with the salt, and then to convert it back into the carboxylic acid, you've got to add a mineral acid to it. Okay, so let's see where we are now. Whoops, not quite the right one. Let's go up here. All right, now we've done that one, haven't we? Right, we've done all of number 1 now. So let's tick that one off. Now, these ones are more sort of typical acid reactions, aren't they? So the first one we'll have a look at is the redox reaction with the reactive metals to produce a salt and hydrogen. This is not hard at all. It's just, the acids acting like acids. Okay. Okay, there's my lithium aluminium hydride. Right. This is just Form 5 stuff even. So we're going to have a carboxylic acid. Okay, and if I react it with a reactive metal, and that means anything above hydrogen basically in the reactivity series. I'm going to get the salt and hydrogen. Okay, so let's pick an acid. For argument's sake, let's pick ethanoic acid. It's the most common. I'm going to react it with magnesium. Excuse me. Right, the salt, the acid is going to lose its proton. So that's the anion that the acid produces. And obviously magnesium is going to lose 2 of its electrons. So it's going to be Mg2 plus. So we'll need 2 of these. And we'll get hydrogen gas. So we need 1 of those, 2 of those, and that. Okay. Now what's this guy called? This guy is called magnesium ethanoate. And obviously this is hydrogen. Now, obviously, you know carboxylic acid is a weak acid. This guy is weak. But it will react with the magnesium to form the salt and hydrogen. It will be a slower reaction than if I use the strong acid, but it will, if it's in excess, it will use up all the magnesium. Now, why does the syllabus call this a redox reaction? It's definitely an acid-metal reaction, isn't it? Acid, it's definitely an acid-metal reaction. But if you look at the magnesium, it starts off as an oxidation number of 0 and ends up as 2 plus. So the magnesium has been oxidized. Okay, now what's been reduced? The hydrogen has been reduced. It's gone from here, where it has an oxidation number of +1 in the acid, and it's gone to 0 here. Okay, and as you can see, if you wanted to balance this using oxidation numbers, you can see. So let me draw that in nicely. There's the reduction. Okay, there's the reduction, and obviously this has gone up by this has gone down by -1, and this has gone up by +2. That's why we need 2 of these, and that's why we need 2 there. Okay, so there you go. So this is a redox reaction, isn't it? Now, I was recently looking at a mark scheme. If you called this reaction on oxidation, okay, according to the mark scheme, you would get it wrong because it's not just an oxidation, it's also a reduction. So you've got to use the term, it's a redox reaction. Okay, so there you go. That's magnesium acting, sorry, not magnesium. That's a carboxylic acid acting as a weak acid, isn't it? All right, we've done a lot, haven't we? Look at this. All right, so we've done the top one there. Okay, let's tick this one off. Now, the neutralisation reaction with alkalis to produce salt and water, I don't think we should need to do that, okay, because it's exactly the same as the redox reaction with the reactive metal, but instead the alkali takes the proton and you get salt and water. Actually, yeah, just let me look at these two quickly in one, okay, because we can knock these off relatively quickly. Okay, so let's do a neutralisation. And then let's do the reaction with the carbonate. Okay, let me keep hiding my lithium aluminium hydride. Okay, all right, first of all, the neutralization. What's a neutralization? Oops, wrong color. Neutralization. Okay, now neutralization is a reaction between an acid and a base, and water has to be formed. Okay, so I'm going to use ethanoic acid. Now, obviously, I'm using ethanoic acid because it's quite small, it's quite quick to draw, but this is the same for all acids. Okay, I'm going to react it with a typical base, sodium hydroxide. Okay, and obviously I'm going to get the salt, which is going to be sodium ethanoate, this guy, plus water. Okay, why is this a neutralization? Well, believe it or not, this is the most important bit. You get water. All right, so you get salt and water, and this particular salt is known as sodium ethanoate. Okay, as you can see, this proton here joins this base here, and that's where you get the water. So the ionic equation for the neutralization would be this: H plus from the acid joins up with the OH minus from the base. Oop, doesn't give that at all. To give me, where are we? Blue. To give me water, and there's the neutralization. Okay, aqueous, aqueous, aqueous. And if any heat came off of here, it would be the heat of neutralisation. All right. It does come off, by the way. This is an exothermic reaction. Okay. So that's acid plus alkali. And on a very similar note, let's do acid plus carbonate, which again, as I say, is a Form 5 thing, isn't it? But we should do it. So that's neutralisation. And then let's do the next one then, a reaction with a carbonate. Okay, which carbonate will I use? I don't know yet. Let's change colours. Let's go for a nice orange. Why not? Okay, so I'm going to use the same acid, ethanoic acid. Okay, there it is. And I'm going to use, I don't know, magnesium carbonate. Why not? Okay, now what am I going to get? Well, if you break it apart, two of these protons, yeah, are going to react with each carbonate there. Yes. So I'm going to end up with, if you think, and this is why I think of it, the carbonate bit reacts with two hydrogen ions from the acid to give me carbonic acid. And then the carbonic acid breaks apart to carbon dioxide and water. Okay, that's how I think of these things. So let's do this then. What are we going to get? We're going to get my salts. You always get a salt if an acid reacts, because that's pretty well the definition of an acid. It loses its proton and it becomes the salt. So in this case, it's going to be magnesium, isn't it? What we're doing, put that around there. I'm going to need two of those for every Mg2 plus. Okay, so this is magnesium ethanoate. Magnesium ethanoate. I'm going to get carbon dioxide and I'm going to get water. What's the balancing like? I think I need two of these, don't I? Does that look reasonable? I think that's right. Two carbons. No, it's not quite right. Do I get two carbons? Right. Oh, I think I need two of those. Actually, I think I need four of these then, don't I? And I get two waters. I think that's right. But I'm sure you can look up the balancing if I've got that wrong. Okay, looks a bit strange, but that's probably okay. All right, so for each carbonate, I need two acids. I've got two carbonates. Yeah, I guess I need four acids there. Okay, so there you go. That's a reaction with carbonates. You get the salts, carbon dioxide, and water. All right. Now, as I say, if I get the balancing wrong, I'm sure you can check that out yourselves and tell me about it. All right, now we've done the bottom bit, or two of the bottom bits. So we've dealt with this one. Let me go back to black. Okay, and don't forget, you can watch the videos on double time to save some time. Eh? So we've dealt with that one and that one. Now, esterification with alcohols and concentrated sulfuric acid. Let's have a look at that. And then the last one is the reduction using lithium aluminium hydride. Okay, which then I can use the picture. That picture. It's very, I don't know why I did it now, because it's only for one thing. All right, so this is the formation of esters. Okay, and this shouldn't take us long because this is something we've done already in Form 5. But how do you get an ester? Well, you get a carboxylic acid. Okay, you react with an alcohol, and you get the ester, and you get water. Okay, now when you're naming this, the alcohol gives the ester, the first name comes from the alcohol, and the last name comes from the acid. Okay, and the ester is that. All right, now this is important. You heat this and you do it with a concentrated sulfuric acid. Okay, actually, I shouldn't put the C there. The C goes in front. We often see like that, conc sulfuric acid, which means no water at all. Okay, if anything, it would be this H2SO4 liquid. So there's no water there, and you heat it. Now you can do this in a test tube, believe it or not. If you just put your acid and your alcohol together, all right, in a test tube, you heat it up. This is our reaction mixture. You heat it up, and there you go, and it forms an ester. All right, now as you will know as well, let's do this a little bit I'm going to use my old friend ethanoic acid, as always, because it's the nice, easy one to draw. The alcohol, I'm going to use ethanol. Okay, there's my ethanol. And as you all know, I'm sure, it is a, there you go, this splits off. Oh, yeah, that's right. There we are. There's my water. There's that. And these two bits join together, all right, to give me my ester. And my ester is going to look like this. Oh, there you go. Yeah, I think I've done that right. Yeah. All right. If you draw this on ChemSketch, it looks like this actually. It goes down like that, not straight. All right. And where was the join? The join came here. All right. Let me do that in a different color. The join came there. So in other words, this bit came from my acid, and this bit came from my alcohol. Okay, this particular ester is going to be known as ethyl, or called ethyl ethanoate. But obviously I've given a simple one, but you've got to be able to do more complex ones than this. And it's known as an esterification. This is an esterification. Okay, and an esterification is when an ester is formed, and it's an example of a condensation reaction. Okay, and a condensation reaction is one where we get the reaction happens and you get a small molecule. Small molecule splits off. They always say splits off. Okay, now it's called condensation because originally they were all water that split off, but it's not. Doesn't have to be water. The other common molecule that splits off is HCl. All right, so that's esterification. So you got to learn that, and you heat them together in the presence of sulfuric acid. Okay, and the very last one. At last I can use the picture. Is a reduction. Okay, now in class we did, if you remember, we had a primary alcohol. And if we had a primary alcohol, we could oxidize it to the aldehyde. And then we'd oxidize that to the carboxylic acid. Okay. Now we can go from the carboxylic acid all the way back to a primary alcohol. This way down, by the way, is oxidation chain. This is oxidation. So going back up the other way must be reduction. Okay. Now, the carboxylic acid can be made to form the primary alcohol if we add this stuff to it. And this stuff, it's very simple, is called lithium aluminium hydride. Okay, lithium aluminium hydride. As you can see, it's a white powder. Now, how is this used? This white powder, you don't want to touch it with water. So what do? We dissolve this, and I don't think you have to know this, but we often dissolve this in an organic solvent called an ether. Okay, so you put it all in a test tube. You have your lithium aluminium hydride. It can't go in water, in ether, and then you pop your carboxylic acid. Okay, the carboxylic acid goes in there, and it converts it to the primary alcohol. Okay, so if you started off with propanoic acid, you'd end up with propan-1-ol. If you started off with ethanoic acid, you'd end up with ethanol. Don't forget, it reduces back to the primary alcohol. Okay, it's got to be a primary alcohol because you can't reduce back to a secondary alcohol because there's a ketone in the way. All right. So interestingly, or not interestingly, whatever your point of view, if you want to go from the aldehyde to the primary alcohol, you could use lithium aluminium hydride because it's a good reducing agent. But we tend to use a more mild reducing agent, and we use sodium borohydride for this one. Okay. But if you want to go from the carboxylic acid to the primary alcohol, you've got to use lithium aluminium hydride. Okay, and there it is. There's a white powder. Right, now let's go all the way up to the top and make sure we've covered everything. I'm pretty sure that's it now. I don't know how long the video is, but it's taking the place of a lesson. So we've saved time in class. Have we done everything here? Esterification, yes, we've done that. And have we reduction by that to form the primary alcohol? We've done that. All right, guys, thank you very much. And I will post this now.